their career. So good job. Up next is our refining technology team. They'll tell us all about process improvements.
All right, we are the refining team, and like Daniel said, our technology basically does two things. One, it increases the yield of more valuable products coming out of a refinery, and two, it increases energy savings. My name is Andy Gill. I'm a chemical engineering senior, and I'm from Sand Springs, Oklahoma.
My name is Sasha Down. I'm an engineering physics major from Chicago, Illinois.
I'm Lindsay McClure. I'm from Tulsa, Oklahoma, and I'm an MBA candidate with a background in industrial engineering.
My name is Joe Oliver. I'm a mechanical engineering student, and I'm from Edmond, Oklahoma.
All right. Well, first thing about refining. A refinery basically processes crude oil, and crude oil is basically a bunch of valuable products that are all mixed together. And so as you pass through a refinery, all these different units separate the different products into the valuable products that you can put into industry and sell for commercial profit. The very first unit in a refinery is called a distillation column or a crude unit, and that's what our technology deals with. So all of the crude oil can pass through this unit, and since our technology is directly impacting all of the crude oil, we can have a direct impact on the amount of money that we can save a refinery. So our inventor is Dr. Miguel Dagenhewitz, who couldn't be here tonight. He is a distinguished professor in this university. He was in the School of Chemical, Biological, and Materials Engineering. And some added incentive, he's quite skilled in the art of judo, so we made sure not to screw up too much.
To do very well. At a high level, Dr. Dagenhewitz's technology, you see here on the right-hand side a picture, a computer schematic of a distillation column. And you have products coming, you have crude oil coming in, and you have products coming out. Dr. Dagenhewitz's technology decreases the amount of the least valuable product coming out of the bottom, the residue, kind of a sludge stuff that comes out, and increases the yield of the more valuable products, gas oil, diesel, kerosene, and it has the added benefit of energy saving. And just an update on the patent that the university has applied for. It's received a notice of allowance, and all the claims that Dr. Dagenhewitz has made have been accepted. We'll be receiving a patent number in less than 60 days. Additionally, our mentors, Tony Fay and Tim McLeod, who unfortunately couldn't be here, they were our team mentors providing this guidance. They work at Clearwater Enterprises, and their subsidiary is Ventura Refining. And they are a great Oklahoma success story. They're bringing up a refinery in Thomas, Oklahoma. It's about an hour west of Oklahoma City. And so in addition to them being mentors, providing us insight into the world of crude oil refining, they also can be our business partners. And so it's a working relationship as well as a mentorship relationship. The benefit for Clearwater or Ventura Refining is that our technology increases their revenue. The benefit for OU is that as a team we get mentorship and guidance, but the university as a whole, they get an in to the oil refining business, which has been part of the difficulty with this technology, is getting that first step inside to the business. And there's a lot of skepticism for new technologies, and so if we can get this in an actual refinery, it lends credibility to our technology. And so Thomas is a really unique opportunity to get our technology to be used in the refining world.
All right. Well, there's two ways that I wanted to validate this technology. And the first way is to use a simulation software that was developed by Simulation Sciences called Pro2. And what we did was you build a simulation of a crude unit without the technology, and then you build a simulation of the crude unit with the technology, and you compare the amount of residue, that least valuable product, in both with and without the technology, and we found that with the technology we decreased the amount of residue, so therefore we are going to increase the amount of profit to a refinery. The second way we wanted to validate our technology we did this semester, me and Sasha went down into a lab in Sarkey's Energy Center, and we used experimentation. They usually ran like 8 hours a day, and we found through all this experimentation that we would decrease the residue without the with the technology by about 15%. So not only were we able to show it on a computer, but we were also to show it with the actual crude oil in a vessel running experiments. So also this semester we mainly Dr. Bagahewitz has been speaking with Ventura Refining and being able to simulate the Thomas Refinery specifically. So we would be able to provide not just general numbers of, hey, maybe we can save you this much, but we would be able to provide them exact numbers of how much money they would be able to save if they were able to use our technology.
All right, now that we kind of have a general idea that the technology works, we'll try to look at more of the economic benefit of this technology for a refinery. So as we kind of mentioned before, there's an expected increase of 10%, well 15%, but to be conservative, 10% of the valuable products, and a corresponding 10% decrease in the less valuable products. Now obviously that can vary. If a refinery is already producing a very small amount of non-valuable products like the residuals, then you're not going to have as much to work with to increase. And on the other hand, if they're producing a lot of non-valuable products, then there's more to work with, and so that percentage may be higher. Now, if you look at a kind of distribution for a refinery on where they get their profit, most refineries in the U.S. make about $10 a barrel on every barrel that's processed. And there's various products that they end up selling, as Andy and Sasha both mentioned earlier. And so this is just a typical or a possible scenario for a refinery. Obviously, there's a lot of other products that a refinery can produce, and they can be in different proportions. But if we take this as a baseline case and say, this is the profit you're getting from each of those specific products, and then we can kind of see how our technology is going to impact those profit margins. So what you can see on the bottom graph there is it may not look like much, but you're actually getting a decrease in the least valuable product. In this case, the least valuable product produced is the gas oil. It's not always the case, but for this case it is. And then you're seeing a sharp increase in the next product up the line, which is the diesel produced. And so that 30, and when in the end, it ends up to about 20 cents more per barrel. So instead of getting $10 a barrel, you're getting $10.20. I know 20 cents doesn't sound like a lot, but because of the volumes that these refineries are doing, it really does add up. So what you can see on this slide is 20 cents a day, or 20 cents per barrel, ends up in almost $25,000 daily increase in the refinery's profit margin. And so if you consider the average refinery size in the U.S. is roughly 120,000 barrels, that 20 cents really does end up going a long way. And then if you expand that farther and look at the yearly basis, you're making $8 million to $9 million additional revenues with these conservative estimates. And so although it may not seem like much at first, this technology really does have a very big impact on the bottom line of any refinery.
Okay, so now that we kind of have an idea of the value of this technology, our next step was to look at the market that we want to take the technology to. And as we mentioned earlier in the presentation, the technology actually applies to any distillation process, but we're specifically looking at crude oil refining. And so to get information on that market, we went to the Energy Information Administration. And from there, we gathered data on U.S. refineries and their total outputs from 2005. And we also looked at the breakdown of the different products they produce, how much and what kind, and then also their units, or their types of hardware, if you will, in the refinery. Some refineries have something called a vacuum column and some don't, and that will affect the implementation of this technology, and so we had to consider that. So after looking at the macro market, we broke it down into different segments. And this graph has a lot of information on it, but really the big picture that I want you to see is that the market that we're looking at that this technology applies to is a wide range of refineries. We go all the way from 20,000 barrels a day being produced all the way up to several 100,000. And so there's a wide range of potential customers that we're looking at when we talk about marketing this technology.
When you're talking about marketing, we're actually working on a license agreement with Ventura. We're right now kind of formulating how that's going to look, but it's going to be a non-exclusive license for them to kind of try out this technology in their refinery. So not only does it hopefully increase their revenues, but it also provides a proving ground for our technology, whereas if we had to kind of do that on our own, it'd be a very expensive process of kind of putting together a pilot plant, and it wouldn't be as accurate as a real-world working refinery would be. And so this team actually has a unique situation where we'll be continuing on to next semester. The CCEW group, there will be a CCEW group next semester working on this same project. And so what you're going to see is they're probably going to be working on evaluating what's the best business approach for this technology and where to take it. But we'll talk about it a little bit more, and we'll talk about that a little bit later. So.
Okay, so hopefully so far we've given you some idea of what we really have accomplished in the last few months. As Andy and Sasha described earlier, the technical validations are a huge part of making this technology, getting it out into the marketplace, and we did that both through computer simulations and the actual experimentation in the lab. And then the second thing we did, as Joe talked about, was creating a spreadsheet that kind of calculates a basic costing model for what it would take to implement this technology, what it would cost, and then also the end payout and an approximation of that. And some of the market data that we looked at will help in creating almost like an individualized pitch book for each refinery, so that we'll be able to tell based on what they make and by how much they make, how much this technology will improve their process. And then, of course, the last thing that we worked on was the Thomas Refinery and getting the technology implemented there, and starting to work on negotiating a licensing agreement with that. And so, as Joe mentioned, next semester there will be another CCEW team that takes this project over, and these are just a few things that we feel like that we would recommend that team focus on in the spring semester. The first, of course, is the completion of the Thomas Refinery implementation and everything that goes into that. The second would be to investigate the best business model for this technology. As I showed you earlier, the market for this has a wide range of small refineries all the way up to very large ones. And so determining the best way to bring this to market is going to be a big priority. The last thing would be to investigate forming a technical support business, and we would recommend that the next team really work closely with the inventor, Dr. Bagahewitz, on this to really capture his vision on what he's looking for in a support business. We really feel like the next semester's team, we're confident that they'll do well in continuing to bring this technology to market. We're excited to see what they do.
And we'd like to acknowledge CCEW and the OCD for the existence of this program and all the great support they've brought to it. From Ventura, we'd really like to thank our mentors, Tony Say and Tim McLeod. And from the School of Chemical Biological Materials Engineering, Dr. Bagahewitz, the inventor of this technology, and Alan Miles, the machinist in the school who helped us with a lot of the nitty-gritty of this experimentation. And from the Coffeyville Refinery, Jeff Thompson, who provided us insight into the refining market, its segmentation and entry into the market with the new technology. If there are any questions, we'd love to take them.
Is this technology a piece of equipment or is it a process?
It's a process that requires equipment, I guess.
Yeah, that's
So it is new equipment.
Yeah, without, there's some equipment.
It would require capital costs by the refinery to implement this process.
But the capital costs are, compared to the profit the potential profit capital cost is somewhere between $100,000 in that range, maybe $200,000. So you're not, comparatively speaking, it's still an easy call. So that's something the next team will have to work on, really narrowing down. So.
You guys have a great point of reference, but what do you think about having your primary mentor having a business interest in the outcome of the technology versus our team and the other teams had mentors who were in it or didn't have a personal stake in the outcome of the project? I
really liked it. I thought it added a different dimension. I mean, I don't think there was a conflict of interest